All right, well, let's move along here and let's look at solving absolute value inequalities. And this ties directly to example 3 in your textbook on page 43, where we're going to do a one-step absolute value inequality. Now, we're talking about inequalities. That tells us we're going to have either and or statements. And when we were looking at compound inequalities, we could recognize the and because it may say and occasionally, but more often than not, you're going to see an expression sandwiched in between two inequality symbols. And the or statement in a compound inequality, you're just going to see or. Now with an absolute value inequality, because we're going to set up two cases regardless, we can really get a clue whether we're talking about an or statement or an and statement by the inequality itself. So the two we're looking at right now are both less than. And so if I go less than, the less thans are going to be and statements, whereas the greater inequalities are going to be or statements. So let's tackle this first one. And there's going to be a couple of other special things about absolute inequalities when we go to solve for the solution set. Now we're going to start first. We're going to set up our two cases like we would on an absolute value equation. And here I'm just going to have t is less than 6. That's my starting point. And then I'm going to have t, and I'm going to put negative 6 out here. But there's something else I've got to do on an absolute value inequality when I'm solving for the solution set. When I set up that second case, not only am I going to set that, in this case, the 6 to a negative, but I'm also going to reverse or flip the inequality symbol itself to make it to read t is greater than negative 6. So we start off absolute value of t is less than 6. We know that whatever's inside that absolute value symbol could be a positive or a negative number. And when it comes out of the absolute value, then it's going to become positive. And so when we set up our second case and we set the right-hand side of the inequality to a negative, we also have to reverse the inequality symbol. Now let's graph this. So let's say we got negative 6 out here, and we got 6 out here. So on one hand, we said that t was less than 6. That's going to tell me I got to have an open dot. Got an open dot right there. And t is greater than negative 6. And I'm going to have an open dot up here. Now, why do we have to do that? We have to do that because the absolute value of a number is its distance from 0. That's really what we're measuring, is what is the distance from 0. And in this expression, or this inequality, t, the absolute value of t is less than 6, well, we're measuring from 0, 6 on either side. And so this makes this work out. And my solution is right here, from 6 to negative 6, but not including 6 and negative 6. And that is my solution set. Now, our book doesn't talk about testing intervals, but later on we'll do a lot of testing of intervals, or we'll see where we need to test intervals. And I can test, so I have 3 intervals here. I got an interval right here. I got an interval here between the negative 6 and the 6, and I've got an interval beyond 6. And I could test any number in those intervals, and if that gives me a true statement, that is included in the solution set. And if it doesn't give me a true statement, then it's not included in the solution set. So let's just say I want to come in here and I'm going to say, okay, well, what about negative 7? Well, if I substitute negative 7 in for t, absolute value of t, well, the absolute value of negative 7 is 7, and 7 is not less than 6. And so that interval fails. Now, I could pick a number here between negative 6 and 6. Why don't I just pick 0? Well, the absolute value of 0 is 0, and 0 is less than 6, and so that interval passes. And what about this third interval? Well, I'm just going to pick positive 7, and absolute value of positive 7 is 7, and 7 again is not less than 6, and so that interval fails. So that's another way of double checking when you're graphing an absolute value inequality. Establish the intervals, test a value in that interval, and see if that gives you a true statement. If it does, then that's part of your solution set. If it does not, then that's not part of your solution set. And so this is a way of proving that this is, in fact, our solution set. Now let's take a look at the absolute value less than -3. Well, here's a rule. If we've got an absolute value that's less than a negative number, this is going to be different on greater than, but if we've got an absolute value less than a negative number, then this is going to be an empty set. There is no solution. Not any number that the absolute value, we can put in the absolute value symbol and it come out to be -3. Now we're going to look at a couple of greater than one-step absolute value inequalities. Okay, so here we got absolute value of t is greater than 3, greater, so we know we're dealing with an or statement. We're dealing with the union of our solution sets as opposed to a less than, an and statement, which is the intersection of our solution sets. So let's just set up our two cases. So I'm going to have t is greater than 3, and then I'm going to set t, in this case I'm just going to put -3, and what have I got to do again? I've got to flip, rotate, invert, whatever word you want to use, reverse that inequality symbol, and let's see, it's going to be t less than -3. So let's get my number line out here. I'm going to set this at 3. Let's say -3 is sitting out here. Okay, so greater than 3, well, that's an open dot, I know that. And greater than 3 is going to take me out to the right. Sorry about my sloppy lines. And then over here on the right-hand side, I got t is less than -3. So I got another open dot. And then to the left of -3. But once again, I've got 3 intervals here. So I got an interval here, I've got an interval here, and I've got an interval here. And if I wanted to make sure I got my graph right, I could test an interval, a number that's within the interval. So let's just say right here I'm going to test -4. Well, absolute value of -4 is 4, and 4 is greater than 3. And so that interval checks. That's a good interval, and I've got it marked as such. Let's pick one in this interval. Let's just say 0. Well, the absolute value of 0 is 0, and 0 is not greater than 3, so that interval fails. And I've got that set up that way. I do not have that in my solution set. And we might as well go ahead and test the third interval, although we know we're right. Let's say +4. Well, the absolute value of +4 is 4, and 4 is greater than 3, and so that interval passes. And so I've double-checked my work to prove that I have graphed this on the number line properly. Now, let's look at this next one. And this one's got a little bit of a trickiness to it because you might see this -2 sitting out here and say, oh, that's going to be an empty set. But not so fast, because that's a greater than. So let's think about this. So I'm going to go ahead and put this in 2 cases. So we got to have u is greater than 2. And this is a greater, and u is less than, oh, that's -2, greater than -2, right over here. U is greater than -2, and u is less than 2. Now, here's another rule. If it is a greater than inequality for an absolute value inequality, it's not an empty set. It is actually all real numbers. Now let's prove that using our number line and our interval. So let's say out here I've got 2, and over here I got -2. I've got 3 intervals here. So let's pick a number here to the left of -2, and I've got -3. All right, so absolute value of -3 is 3, and 3 is greater than -2. And so this interval right here would pass. Let me relabel this 1, 2, 3 for these intervals. All right, let's pick a number here between -2 and 2. In that interval, let's pick 0. Well, the absolute value of 0 is 0, and 0 is greater than -2. And so that interval will pass. And over here in the third interval, let's pick 3 as our test point. And so we've got the absolute value of 3, where the absolute value of 3 is 3, and 3 is greater than -2, and so it passes. And so this is a proof that my solution set is truly, in this case, with an absolute value greater than, even though it's a negative number, my solution set is all real numbers. There's some tricky things about absolute value inequalities that you got to pay attention to. Be a good thing to take notes on. Go back and review this video. Look for the unusual type statements I'm making about absolute value inequalities and make note of them, and it'll help keep you from making a mistake in your homework and most of all in your test.